Okay, so I think it's just about time, so I'll get started. Thank you very much for being here. My name is Bilar, and I'm going to talk to you about, well, the computer lets me. I'm going to talk to you about a common problem that we have when we want to identify and classify specific specimens of software. On the one hand, you want to do it quickly, but you also want to do it exactly. So you want to have your cake and eat it too. The problem with most approaches is that they either fall squarely on one end of the spectrum and on the other one. What I propose is just a modest approach. In German, you call it the Denkanstoß, which means something to think about. Namely, using statistics, which is a form of aggregation of data, some would even say a form of compression, that is a little bit more resilient to common obfuscation techniques so that we can, with reasonable accuracy and reasonable speed, quickly identify and afterwards classify malware. So the idea behind the three approaches that I'm going to show you today is very handily represented on the state-of-the-art graph. On the lower left-hand side, you see signature-based approaches. They are quite fast, they're quite exact, but they're relatively sensitive to permutations, they're relatively sensitive to all sorts of these obfuscation techniques that you deal with. On the other hand, you have emulations and heuristics, which is, and I figured this out during my training, more for black art than it is a science. You have to rely on a lot of implicit knowledge. I mean, you have to know this. It's hard to codify, and it takes you potentially a very long time to go through this. So what I'd like to find is a sweet spot, like Goldilocks. Not too cold, not too hot, but just right. Just the right amount of simplifications that we have a little bit more obfuscation tolerance, and yet we retain some of the speed that we've had before. And the vehicle which I would like to explore this, I call statistical structures. No, I mean, you can call it whatever you like. I just wanted something that had some alliterative meaning to it. There are three approaches that I looked at. One was taking the perspective of the opcodes. We built a frequency distribution and built, from this frequency distribution, a fingerprint. The statistical structure there is the frequency distribution of the opcodes. I did it primarily through static disassembly, but there's no reason why you couldn't do this through memory, taking snapshots. The other one is the time-tested and true Win32 API call sequencing. So what you do is you observe the API calls, you put them in a call vector, in a vector space model, use a simple similarity function to compare them to other known families, and then you can classify them. Very simple model, had surprisingly good results, I had to say. The third one is graph-based. If you don't know much about graphs, no worries, I'll give you the 2-minute primer. The idea here is that programs can be represented through a very powerful framework, which is called a system dependence graph. It captures control, flow, and call functionalities in the graph, and we can extract certain features of this graph. And I'll talk about those features in a little while. Again, construct a statistical measure on it, and try to use this for classification and identification purposes. This is the one-slide synopsis of the fingerprint analysis. In essence, again, you tally up the opcodes of the specimen that you have there. You build a statistical profile, and you start comparing them to, let's say, what I call goodware, because non-malicious software was too long to fit on the slide. Good software against bad software, and see whether you can find any discrepancies. Again, statistics are a nice vehicle because statistics are relatively robust under permutations. If you take, just as a very simple example, if you take the average of 1, 2, and 5, you get the same thing as the average of 2, 1, and 5, even though the order is permuted there. The main result I got here is that rare opcodes explain much more variation than the common ones, and I'll show you this in a second. A word about the procedure. I fired up my old Osborne 1, and I inventoried all the PEs, and there I ran them through. I took a random sample. I ran them through IDA with the customized instruction counter plugin, which also recorded some meta information. The important stuff on the slide is right around here. Gave me out the compiler. I wanted a few more factors. This I put in by hand. What kind of type of software it was. This is just my own taxonomy. The meat of the instruction counter is here. Gives you a ranking. The number of the opcodes. 20% were mobs in this particular program, and there were 2,000 of them found, push calls, and so on. I parsed this, and then I fed it into Excel and did some statistical analysis on there. For the malware, I took a few more precautions because I listened to Jason Geffner and Scott Lambert, who told me always do this in a virtualization environment. So I did this in VM Player. I again ran it. The only difference I did here, as opposed to the goodware what I call non-malicious software, is that I fixed 7 classes. I wanted to also see whether there are signatures that differ across classes. So rootkits, Trojans, backdoors, tools, bots. I just assigned this malware to these 7 classes. Again, I did the same procedure, and I put the data into Excel. If we look at one of the first results, just this old pie chart. Normally I hate pie charts because they're a waste of ink, but this here shows you something interesting. So we're about 400 opcodes or so. We found about half of them. About 72 opcodes cover practically everything. 2/3 of all counts are covered in the first 5 opcodes, and 14 opcodes cover over 90%. And as you would expect, Malware is in there, and push, and call, and pop, and so on. This is for the good software. For the malware, and this was aggregated, and these were 67 Ps, this again class block from my 251s, we have a similar picture. We have, in the top 5 opcodes cover about 2/3. We have the top 14 over 90%, and the top 60 100%. I found 2 undocumented ones, which then, in hindsight, showed me, rare opcodes do carry some information, but more of that later on. This slide, how do you parse this? You see on the outer rim, this is the aggregate malware, and on the inner rims, these are the class blocked ones. I don't know if you can see this from the background, but I anticipated this, and I have a zoom tool. So the second most outer ring is the worms, the third most is the virus, the fourth is the Trojans, bots, tools, then rootkits, user rootkit kernel. Okay? Now, from this slide, you should only take that. You see there are some discrepancies in the very common ones, but as we go down here, they seem to the distribution frequencies and occurrence seem to kind of converge here. Now, if I tally this up, this is completely unintelligible, but I just wanted to say what you get here. This is kind of breakdown. How do you read this? These are the top 14 opcodes, the 14 most frequent opcodes. This is my baseline, goodware, right, the non-malicious stuff, and this is for the other classes. And we can see here, they are the viruses used on average 16% were mobs, 22% were push, and so on, as opposed to goodware, 20% push, 8% were calls, and so on. The key here was that this is a frequency distribution. Now I would like to see whether I can run some tests on this and answer a simple question, namely, given that I have this opcode frequency distribution, is there any significant difference for malware in this kind of distribution? So I'm looking at the distribution of the goodware and the malware, trying to figure out, is there something other than chance that could explain discrepancies or similarities? So on the left there, you see my baseline. What I did was, for the statisticians among you, I did a consistency table test, chi-square testing with Huberin star residual test. What I got here, that's statistical thingamajig. How do you parse this? Well, it's a little bit hard to parse, and most of the explanation will come in the next slide. What you can see here, what you should get from the slide is just, I color-coded it for visual convenience. Whatever is darker means higher or lower higher or lower discrepancies. Whatever is white seems to be kind of similar. Whatever is darker red or darker blue seems to be different. So we can see here that the kernel rootkit, for instance, has practically everything. Everything seems to be significantly different from the normal stuff. Tools seems to be kind of, roughly, 2/3 and so on. Worms, for some odd reason, like that too. I don't know why. So what I showed you on the previous slide was there is, according to the tests, and again, it's a statistical test. This is not, the word of God coming through Moses. All this thing tells you is that from this test, this is what it tells you it's significant. There's another statistical test you can run. It's called Kramer's V. What Kramer's V, and this is the top line here, tries to say is, listen, okay, you figured out that there is an association between the column and the row variables, between the classes of software and the frequency distribution. But how much of the variation of the data does it explain? And what we find here from this slide is that just 5 to 15% of the variation is explained actually through this association. So this is not a very good predictor. So what you get from the slide is the top 14 opcodes, the most common opcodes, are not a good predictor to be able to say this piece of software belongs to goodware or to any of the malware specimens. I have here a few hypothesis why I see these discrepancies that I see in the testing. People with much more knowledge than I do can probably figure out much better reasons why this is, but these are just my thinking on it. Sampling the horse from the other end. Let me look at the rarest opcodes. This is a sampling of the rare opcodes. They're so rare that I couldn't get them any more in percentages. I had to get them in parts per million. So these are samples, so this is out of 1 million opcodes, 37 will be FDiv P, and 260 will be NOPS here, and 20. This is all from my samples. Again, I ran this. I did again the chi-square test with the star residuals. And what I found here is, again, the most interesting part here is, again, Kramer's V tells me that although I don't see in many categories a statistical significant deviation, and those that I do see, it does explain, anywhere between 12 and 63% of the variation, depending on where I am. This may be an artifact of selection sampling bias, or this may be a real effect. I'll have to investigate it further, but it conforms a bit to intuition that they try to be a bit evasive, have some instruction substitution. All these little obfuscation tricks that you learn from Atam's book, or that you learn from Zohr's book on malware research, you may find this in there. Okay. So what I would like you to get from this first third is the rare opcodes carry more information, seem to carry more information that can be used for classification and identification purposes. There are, of course, further directions. I added a few more categorical data when I did the inventorying with IDA. I can still study. I studied this in a two-way contingency table. One way was class, and the other one was opcodes. I could have a third or fourth dimension for compilers. Compilers may produce a pattern that you should investigate. The 3 or 4 or 5 common compilers. You can start expanding. Common opcode nuggets. There will be a size between basic blocks and isolated opcodes, and of course, try to attack the scheme. Specifically with the purpose of defeating it, which I haven't done yet. Now, if you want to see some related work, I can recommend these 3 papers and so on, and a few more references at the end. Now, this was more for identification. Let's see if we can find classification. This is work that I did with my honor student Chris Rees, who's now at Vigilant Minds, a year ago or so. So the key procedure here is we run the stuff, we record the API calls, we construct a fingerprint from the API calls, not an ordered sequence, just the mere fact how many times are they called, put them in a database, and then cross-compare it using a similarity measure. The interesting thing was that this relatively simple model, I thought to myself, Chris, we'll start like this, and then if it doesn't work, we'll go to finite state automaton, yielded surprisingly good results. I mean, 80% for a first stab, where you don't have to do very much, is not bad. I mean, at least for me, it's not bad. If the weather forecast was 80% right, I'd be very happy. High-level overview of how we did this. Data collectors, we build a vector from the API calls. We dump them to the database. We used a comparison, and we then assigned it to a family. Again, the goal here was classification of malware that we knew was malware, but we didn't know which family it belonged to. We wanted to see whether we could classify them just with the API calls. How did the data collection work? We set up, again, fake environments. We faked the network. There was a DNS server and so on, so they thought that we're in there. The relayer, we logged the file into the console, so we can have a look at it. What did we do? We used inspiration from the Microsoft Detours project. We hooked the functions. We injected into the process address space. We hooked the functions and just recorded. Okay. I invite you to look at the Microsoft Detours project for more details on this. What is the actual data we recorded? This is an illustration. So it's a vector. Think of a vector, 1,200